We've looked at a lot of cumulative change so far functions. When we started with a constant function, we got a linear total change so far function. When we started with a linear total original function, we got a parabolic looking cumulative change so far function. We didn't really verify it was a parabola. When we started with sine, when we started with cosine, we got sine. When we started with sine, we got negative cosine plus 1. When we started with e to the negative x, we got something that looked like an upside down e to the negative x. So it's seeming plausible that there's a derivative kind of thing happening here somewhere. So the fundamental theorem of calculus part 1 says that the derivative of big F is the total change so far function, is little f, the function that we started with. We've kind of gathered lots of evidence that that's reasonable. So how can we put prime and equals or something here? Can I just write equals? No, that's not true. Should I put the prime here or there? So it says the derivative of big F, so that would be putting the prime here, is little f. So another way to say that is big F the derivative of little f? No, it's the opposite. So big F is the well, let's say it's an antiderivative of little f. I'm saying an antiderivative because we don't really need to say which one. We don't need to say what that shift is, because we would just take the derivative right away and see that we get the original function, and that vertical shift would go away. So here we're not worried about which antiderivative it is. The fundamental theorem of calculus part 1, most statements of it require the original function to be continuous. The cumulative change so far has a derivative everywhere. But sometimes we want to apply fundamental theorem of calculus stuff to discontinuous functions. And it doesn't mean that the integration just totally fails. It just means that it might fail at those discontinuities. So here's some bonus fun suggestions for you. We're not going to take time to cover them. What if your original function is the Heaviside step function, which you can type into Desmos this way? What do you get for big F of x? Try sketching it, see what Desmos tells you. And then extra bonus, what if your original function is a square wave? And here's an interesting way to do a square wave. Try sketching what big F would be. So these are two useful non-continuous functions that hopefully have some kind of cumulative change so far curve. All right, that's FTC part 1.